Somewhere far beyond the horizon of what we see each night, past a veil of quiet stars above your head, there drifts a secret unlike anything on Earth. Not a planet, not a comet, not even the sun as we know it. Out there, in the cold silence of space, floats a diamond, not a gem held in a jeweler's hand, not a glittering stone locked in a crown, but a diamond the size of a planet. If you close your eyes, imagine that for a moment, a crystalline sphere, vast as Earth, forged not in mines, but in the heart of a star. Take a breath, let yourself sink into that picture. And while you rest there, listening to this quiet story, let me gently invite you, if you'd like to join more journeys like this one, exploring the strange and the soothing corners of the universe, you may like to follow along, to subscribe, to leave a small trace of your presence. Think of it as leaving your footprints in the sand of a cosmic beach. Now, let's walk further together. This cosmic diamond has a name. It's formal. Astronomer-approved title is BPM 37093, though scientists found a softer nickname. Lucy. Lucy, after the Beatles song Lucy in the Sky with Diamonds. A quiet wink of humor from people who spend their lives studying the void. Lucy is not unique. Astronomers suspect many such crystallized stars exist, but Lucy is the most famous. She lives about 50 light-years away in the constellation of Centaurus. That's not so far on cosmic scales. If you try to drive there at highway speeds, though, you'd still need millions of years. Even with a rocket, you'd be traveling long after your great-great-great-grandchildren stop remembering your name. In other words, Lucy is close enough to know, but forever out of reach. What exactly is Lucy? She is what's left when a sun-like star exhausts itself. Stars live by fusing hydrogen into helium. That process is like a cosmic fire. It produces light, heat, and a gentle outward push that keeps a star inflated. But stars don't burn forever. When the fuel runs out, the balance collapses. A star like our sun swells into a red giant, grows unstable, and sheds its outer layers. What remains is a star's core, a compact husk called a white dwarf. Now, white dwarfs are already strange. Imagine squeezing the mass of the sun into something about the size of Earth. The density is so extreme that a teaspoon of white dwarf matter would weigh as much as a mountain. If you try to scoop it up, it would slip through your hand, crushing everything beneath it like an invisible boulder. Lucy, however, took this oddness one step further. Over billions of years, her carbon and oxygen atoms cooled and began to align into crystalline structures, just like diamonds form under pressure here on Earth. Except on Earth, diamonds fit into rings or necklaces. Lucy is a jewel the size of an entire planet. You could say it's the universe's most extravagant engagement ring, waiting for someone reckless enough to claim it. Of course, no one ever will. Even if humanity somehow reached her, Lucy's gravity would be so intense that a human body would be flattened in an instant. So she shines there untouched, a treasure no one can ever hold. Picture this. You're standing, somehow, on a platform hovering just above Lucy. You look down and what you see isn't rock or soil or ice. You see a hard, crystal surface stretching in all directions. The light of nearby stars reflects faintly, as though on frozen glass. There is no sound, no breeze, only the silent weight of eternity pressing down on a jewel larger than worlds. It's almost funny. On Earth, we celebrate diamonds as rare. People save fortunes for a single polished stone. Yet here, floating in the depths, is a diamond so vast that it mocks our obsession. Lucy doesn't fit into anyone's jewelry box. She is a reminder that the universe does not measure beauty in carats. How do scientists know she exists? The answer lies in a delicate trick. White dwarfs like Lucy sometimes pulsate. They tremble with faint vibrations, like a giant bell struck in silence. Astronomers can measure those vibrations, and from the way they travel through the star, they can infer the structure inside. That's how they found a crystalline heart. Billions of trillions of carbon atoms locked together, waiting in the cold. And Lucy isn't alone. Some researchers believe that, in time, every white dwarf in the universe will crystallize. Stars like our sun may all leave behind diamond hearts, which means the future cosmos could be filled with jewels, frozen reminders of light that once shone. Perhaps billions of years from now, galaxies will glitter not with burning suns, but with cold, crystalline corpses. A quiet jewelry box in the dark. It's beautiful, it's eerie, and it shouldn't exist, but it does. Let us step gently onward. Far from Lucy's quiet shine, there's another world, but this one burns. While Lucy is a frozen gemstone, calm and crystalline, KLT9b is chaos incarnate. Imagine a planet hotter than most stars. That's KLT9b. This world orbits so close to its host star that its atmosphere is more like boiling soup than air. At temperatures over 4,000 degrees Celsius, molecules can't hold themselves together. They break apart into individual atoms, drifting and colliding like unruly guests at a wild party. Iron vapor floats through the air, titanium vapor as well. It's as if the entire planet turned into a blast furnace where the periodic table goes to riot. And here's the absurd part. The atmosphere isn't just hot, it's evaporating. KLT9b's star blasts the planet with ultraviolet radiation, so strong that the gas is literally streaming away into space. Think of it like a comet, with a giant tail trailing behind. Except this comet is made of hydrogen, and the tail is so massive that the planet loses millions of tons of atmosphere every second. If you try to stand there, which you wouldn't because there is no surface, you'd be shredded instantly. Even atoms have trouble surviving on KLT9b. Yet, improbably it remains, slowly wasting away, but stubborn, glowing like a lantern about to burn itself out. Some scientists predict it may not last. One day, KLT9b might vanish, swallowed by its star or stripped into nothing. But for now, it exists. A planet too hot to make sense, too unstable to endure, and yet there it is, circling endlessly. Pause for a moment and let yourself feel the contrast. Lucy, a frozen diamond. KLT9b, a boiling world of vaporized iron. Two opposites, one solid and eternal, the other gas and flame, both, in their own way, proof that the universe writes stories far stranger than human imagination. In the stillness of your room, you may feel the weight of this journey. Out there, things exist that make no sense by earthly logic. A planet that shines like jewelry, another that evaporates like steam. And this is only the beginning. The cosmos has stranger gifts to show us. Now imagine a galaxy. Vast, sprawling, made of hundreds of billions of stars. Each star with planets, some dead, some alive, all wrapped in gravity's invisible embrace. Galaxies, as far as we've learned, need something unseen to stay together: dark matter. Dark matter is the scaffolding of the cosmos. Without it, gravity alone would be too weak to hold such immense structures. The stars would drift apart, like glitter spilled into water. And yet, there are galaxies we found that seem to be missing it. Think about that. Whole cities of stars, spiraling quietly in the dark, apparently held together without the glue of dark matter. If that's true, it means one of two things. Either the universe is playing a prank on us, or our understanding of physics isn't as solid as we thought. Scientists have tried to explain it. Maybe these galaxies were stripped of dark matter by violent encounters. Maybe the measurements are misleading. Or perhaps gravity itself behaves differently on the larger scales. A theory called MOND, Modified Newtonian Dynamics, suggests that at galactic distances, the familiar laws bend. It's not a theory that wins many popularity contests, but galaxies without dark matter make it harder to ignore. It's like seeing a bird fly without wings. Either the bird is hiding something, or your definition of flight needs revision. The universe has a way of embarrassing us that way, reminding us that the story isn't finished. Let's step away from the dizzying scale of galaxies and move toward something smaller, but no less mysterious. A moon. Not Earth's moon, though. This one circles Saturn. Its name is Titan. From a distance, Titan looks dull, a hazy orange ball, cloaked in thick clouds of methane. But beneath that disguise, Titan holds surprises that keep scientists awake at night. For one, Titan has lakes and rivers. They're not made of water, but of liquid methane and ethane. Imagine standing at the edge of the shoreline where the waves are not water, but chilled hydrocarbons, lapping under a golden sky. If you struck a match there, which you couldn't because oxygen is missing, the whole place would ignite into a firestorm. But in Titan's frigid air, it all rests calmly, a frozen parody of Earth's coastlines. And then comes a deeper mystery. Beneath Titan's icy shell, evidence suggests there may be a hidden ocean. Not methane, but water. A salty ocean, locked away under kilometers of ice, warmed by the constant tug of Saturn's gravity. That means Titan might hold two oceans, one alien and one familiar. It's a strange thought, standing on a shore of liquid methane, knowing that deep below your feet lies a second sea, dark and hidden, where water sloshes in silence. Could life exist there? It's not impossible. If Earth's deep oceans can harbor creatures near volcanic vents, feeding on chemical energy without sunlight, why not Titan's secret waters? In a quiet way, Titan seems more alive than it should be. Not alive with people, of course, but alive geologically, atmospherically, chemically. It breaks the rule book of moons, and in doing so, it reminds us that our tidy categories, planet, moon, habitable, dead, are only rough sketches. Now, from icy stillness to a world of violence, let's look at HD 189733b, though perhaps it deserves a nickname less sterile. If Dante had written an inferno for planets, this one would be in the deeper circles. HD 189733b is a hot Jupiter, a gas giant like Jupiter, but scorched because it clings close to its star. So close, in fact, that it completes an orbit in just 2 Earth days. That's 30 times closer to its sun than Earth is to ours. What does that mean for weather? Well, here's where things turn nasty. Its skies are blue, yes, but not the gentle blue of our daylight. These skies howl with winds blowing at thousands of kilometers per hour. Winds so fast they make Earth's hurricanes look like a child blowing candles. And the rain, yes, it rains there, but not water. On HD 189733b, the rain is made of glass, microscopic shards of silicate, blasted sideways by supersonic winds. Imagine stepping outside into a storm that slices instead of soaks. It is beauty sharpened into cruelty. If Dante could walk among planets, this is where he'd write another verse. But HD 189733b is not in a poem. It's real. A place in space where skies cut and winds scream, and survival is as impossible as standing inside a furnace filled with shattered windows. And yet from afar it looks calm, just another tiny flicker of light, indistinguishable from the stars. That's the irony of the cosmos. The most violent things hide behind ordinary twinkles. We drift onward, from planets and moons to something stranger still, dark energy. Where dark matter holds galaxies together, dark energy pulls them apart. It's not something we see. It's something we infer from the way the universe expands faster and faster. Think of it as a cosmic feedback loop. The more space expands, the more dark energy there seems to be, and the more it pushes, like a balloon that not only inflates but accelerates as it grows, without anyone blowing into it. Gravity still works, of course, on local scales. It pulls matter into stars and galaxies. But across billions of light years, dark energy wins. It stretches the very fabric of the cosmos. Eventually, it will pull everything apart. Galaxies, clusters, even the faintest structures will drift beyond reach. And here's a haunting part. One day, distant galaxies will vanish from our sky, not because they disappeared, but because their light will never reach us. Future astronomers may look out and see nothing but their own galaxy, alone in the dark, unaware that others ever existed. We live, right now, in a lucky window. The universe is still transparent enough for us to see far, to glimpse its size, to understand that we are not alone. But this window will close. In trillions of years, the night sky will shrink, and the universe will seem static, cold, and solitary. That, too, feels like something that shouldn't exist, but it does. From the vast to the compact again. There's a star called PSRJ 1748-2446 AD. Its name may sound like a password, but its behavior is far stranger than numbers suggest. It is a neutron star, the collapsed remnant of something once immense. Neutron stars are already absurd. A city-sized sphere cramming more mass than the sun, made almost entirely of neutrons. They're so dense that if you dropped a marshmallow onto one, the impact would release more energy than an atomic bomb. Not very friendly places. But this one spins. And not slowly. It spins 700 times every second. That means if you stood on its equator, and you'd be flung around at a quarter the speed of light. It's the fastest spinning neutron star we found, and somehow it holds together. By all logic, it should tear itself apart. A sphere spinning that quickly ought to fling its own crust into space. Yet there it remains steady, humming invisibly in the void, like a record on a turntable stuck on fast forward. It humbles us, doesn't it? A world can boil away. A moon can hide oceans. A galaxy can lack its dark glue. And a star can spin itself into madness. And still, they continue existing. The universe is patient. It does not care whether we think these things should exist or not. They simply do. There are black holes. And then there is TON 618. If the universe keeps a record of excess, this black hole is the signature at the bottom of the page. It is not just big, it is impossibly big, so massive that it strains the limits of how we think black holes can form. TON 618 tips the scales at over 66 billion times the mass of our sun. The number is so large it barely feels real. Imagine every star in the Milky Way, a few 100 billion of them, gathered into one object. That still wouldn't match the appetite of this singularity. And yet there it is, a monster sitting 10 billion light years away, quietly consuming anything foolish enough to cross its horizon. What does a black hole like this look like? We cannot see its heart, no one can. But we can see the violence around it. Matter falling inward heats up into a disk of blazing plasma, hotter than most stars, shining across the cosmos. Quasars, we call them. Cosmic lighthouses fueled not by fire, but by destruction. TON 618 is one of the brightest. If your eyes could see across galaxies, it would glare like a beacon, a wound of light in the fabric of night. Closer to the edge, gravity stretches space so intensely that time itself begins to warp. This is where the rules of everyday life lose meaning. Near a black hole, time runs slow. To someone orbiting close, minutes might pass while outside, years stream by. Step closer still, and the rolls of space and time exchange places. In the equations, time becomes something you fall into, like a well with no bottom. Space becomes twisted, almost irrelevant. And at the singularity, that invisible point at the center, the story ends. There is no stopping, no turning back, no survival. It is not a place, but a fate. Pause for a moment. Picture yourself orbiting TON 618 at a safe distance. Around you, The accretion disk burns with impossible energy. Beyond, galaxies drift silent and calm. But as you draw closer, you feel time drag at your steps. What is a second to you becomes a century to anyone watching. In the quiet, you realize that black holes do not just distort the sky. They distort reality itself. It's unsettling, yes, but also strangely soothing. Here is an object that takes our most certain rule, that time moves forward the same for all, and gently, firmly says, not always. From monsters to emptiness, let us turn to the vast cosmic voids. A void is not a black hole. It is not a region of negative energy. It is simply nothing. Stretches of space so large, so smooth, so empty that they seem like mistakes. Great hollow bubbles, tens or hundreds of millions of light years across, with almost no galaxies inside. And yet they are real. Astronomers can map them by watching how galaxies bend their paths around invisible boundaries. They can measure the faint gravitational tug of what is missing. These void like the silent punctuation marks of the universe, the pauses between crowded paragraphs of stars. Stand at the center of one, if such a thing were possible, and the sky would look thinner. Galaxies would cluster only at the horizon, leaving you adrift in an eerie, dark sea. The emptiness itself would feel heavy, and still it would be beautiful. There is something quietly haunting about knowing that the universe is not full, but patchwork, light and emptiness stitched together. From the emptiest places, let's move to the fluffiest. Yes, fluffiest. Meet Kepler 51b. At first glance, Kepler 51b seems like a normal gas giant, roughly the size of Jupiter. But when astronomers calculated its mass, they found something absurd. It's hundreds of times lighter, a planet as wide as Jupiter, but with a density of cotton candy. If you could scoop a spoonful of its atmosphere, it would weigh almost nothing. Place the whole planet in water, if such a thing were possible, and it would float. The term astronomers now use is ultra-low-density planet. To everyone else, it's the marshmallow world. How does such a thing exist? Theory suggests that intense heat from its star has puffed the planet's atmosphere into a swollen balloon. Or perhaps it's still young, its gases not yet compacted. Whatever the cause, Kepler 51b shouldn't be real. Yet there is, orbiting calmly, a cosmic puffball. It's a reminder that planets don't all fit our tidy models. Some are solid, some are molten, some are frozen, and some are just big fluffy spheres, drifting like soap bubbles in the dark. And now, let's look not at what is, but at what will fade. In a few trillion years, so far into the future that Earth and the Sun will be long gone, the universe will look very different. Astronomers believe that distant galaxies will slip beyond sight. The expansion of space will carry them away faster than their light can travel to us. Future beings, if any remain, will look out the sky and see only their own galaxy, floating alone in darkness. They will have no observational evidence of the Big Bang, no proof that the universe ever expanded, no signs of the grand structures we now chart. To them, the cosmos will appear static and eternal, empty. They will live in a universe that hides its own history, leaving only a false calm. We, today, live in a rare window of time. We can still see the distant light. We can still measure the faint echoes of creation. We can still know that we are part of something far larger. That awareness itself is fleeting. One day it will vanish. The universe doesn't just create strange objects. It also plays strange tricks. One of them is called the dark flow. When we look at galaxies billions of light years away, their motion should, on average, cancel out, randomness smoothed across space. But it doesn't. Instead, whole swaths of galaxies seem to be drifting together, as though pulled by something beyond the visible universe. We don't know what causes it. Perhaps there are massive structures beyond our horizon, tugging at us with invisible gravity. Perhaps our models are incomplete. Whatever the explanation, the dark flow suggests that the universe is not as uniform as we once thought. That even on scales beyond imagination, there are currents, rivers of galaxies sliding in mysterious directions. It's humbling. We live in a universe that not only expands, but drifts. A universe where even galaxies could be carried by unseen tides. And then, a more dramatic sign of what we cannot see. The Bullet Cluster. 2 clusters of galaxies collided here, smashing together in a cosmic crash. Normally, matter should slow down, interact, heat up, but when astronomers observed the Bullet Cluster, they found something strange. The visible matter, the gas and stars, was disrupted, but the majority of the mass sailed through unaffected. That invisible mass was dark matter. The Bullet Cluster gave one of the clearest proofs that dark matter exists. We still don't know what it is made of, whether it's particles, fields, or something stranger, but we know it is real. It pulls without shining. It weighs without touching. It shouldn't exist, not according to the physics we grew up with. And yet it does. It holds galaxies, shapes the universe, and silently slips through collisions as though nothing happened. Now let's imagine something lonelier. The rogue planets. Most planets orbit stars, like polite citizens. But some don't. Some wander freely through interstellar space, ejected from their homes by gravitational chaos, or born adrift. They drift in eternal night, with no sun to warm them, no orbit to trace, no dawn or dusk. And there are many. Current estimates suggest there could be more rogue planets than stars in our galaxy. Hundreds of billions, possibly trillions, each one a cold orphan drifting through the dark. If you were to stand on one, the sky would never brighten. No sunrise, no sunset, only endless blackness, with distant stars frozen in place. A lonely world, but still a world, perhaps with oceans under ice, perhaps with atmospheres thick enough to hold heat. They are strange, they are silent, and they are countless. Planets are usually symbols of stability. Great spheres orbiting faithfully around their stars, holding their shape for billions of years. But not all follow the script. Some are falling apart. Astronomers have discovered worlds so close to their stars that the heat is literally tearing them to pieces. Their surfaces vaporize, their atmospheres peel away, and trails of dust stream behind them like cosmic sandglasses, slowly emptying. These are the disintegrating planets. One such world, known as KIC 125575448b, circles its star once every 16 hours. That orbit is so tight the planet is roasting, its rocks sublimating into gas. With every lap around its star, it sheds more of itself, leaving a dark-tailed debris that dims the starlight when observed from Earth. Imagine walking a beach where each wave carries away a grain of sand beneath your feet. That is this planet's fate, wave after wave, orbit after orbit. Someday it will be gone entirely, erased by the very star that once gave it warmth. It's a quiet lesson in impermanence. Even worlds are not forever. Some moons, though, seem determined to resist. Take Enceladus, a tiny moon of Saturn. At first glance, it looks like nothing, a frozen marble, smooth and white. But then the Cassini spacecraft flew close, and it saw geysers. From cracks near the South Pole, fountains of water vapor and ice particles burst into space, spraying hundreds of kilometers high. Cassini flew through them, tasting the vapor, analyzing the grains. And what it found was astonishing. Signs of salt, signs of organic molecules. That means beneath Enceladus's icy crust, there is likely a global ocean kept liquid by the flexing of Saturn's gravity. A dark sea, warmed by geological vents, capped by ice but open in spirit. The geysers are like messages from that hidden ocean, carried into space for us to read. If we cannot dive beneath the ice, the moon kindly throws samples into the sky. Enceladus should be dead, A small moon, far from the sun, with no reason to hold liquid water, and yet it breathes into the void, a reminder that life's ingredients may be hiding in unexpected places. Not far from there, in thought if not in distance, we encounter another curiosity, the world of two suns. Science fiction has long loved the image, a desert hero staring at twin sunsets. But in reality, such worlds exist. One of them is Kepler 16b. Kepler 16b orbits not one but two stars. From its surface, if you stood on firm ground, you would see two suns rising and setting, sometimes together, sometimes apart, painting the sky in dances of light. Its surface is cold and gaseous, unlikely to host life. But the idea alone is enough to bend the imagination. A sky where shadows overlap, where days stretch strangely, where calendars will be a nightmare to write. Binary star systems are not rare. Many planets may live in the pull of two parents, their climate shaped by the combined warmth, their skies forever alien. A reminder that Earth's single sun is not the only way to light a world. From strangeness of orbits, let us drift into the strangeness of color. Some planets are so hot they should shine brightly, yet when astronomers pointed telescopes at them, they appear dark, almost black. These are the dark exoplanets, worlds that absorb nearly all the light that hits them. The worst offender is Trace 2b, which reflects less than 1% of its star's light. That makes it darker than coal, darker than fresh asphalt, darker than any paint humans can create. Why? Its atmosphere may be rich in chemicals that swallow light. Sodium, potassium, vaporized metals. Together they turn the planet into a light trap. When viewed from afar, it barely glimmers, glowing only from its own faint heat. Imagine flying past it. You wouldn't see a planet at all, just a sphere-shaped absence, outlined only by starlight bending around its silhouette. A world hiding in plain sight, and yet it exists silently orbiting, a shadow among suns. The universe, though, is never content with one flavor of weirdness. Some white dwarfs, those dense, cooling remnants of stars, sit in binary systems, paired with companions. Sometimes they steal matter from their neighbors. They pull gas onto their surfaces until it piles up, and then it ignites. These are recurrent novae, outbursts that flare into brilliance, then fade, then return. Not once, but over and over like cosmic heartbeats. The process should strip the white dwarf, but instead, it sometimes fattens it. Layer after layer of accreted material alters its atmosphere, leaving strange spectral fingerprints, heavy metals where none should be, lines of elements that speak of theft and fire. It is recycling at a deadly scale. A reminder that even dead stars find ways to stir drama into silence. Among the giants, chaos reigns too. Hot Jupiters, those oversized gas planets clinging too close to their stars, often clear their neighborhoods. Their migrations inward may shove aside smaller planets or hurl them into the star itself. This could explain why hot Jupiter systems seem lonely, missing the family of small rocky world we expect. The giant arrived late to the dinner table, pushed everyone else out, and claimed the seat nearest the fire. And because of their inflated atmospheres, hot Jupiters often grow larger in radius than Jupiter itself, despite having similar mass. Puffy bullies, swollen by heat, hogging the spotlight while their siblings vanish. It's cosmic slapstick. If planets had personalities, hot Jupiters would be the loud uncles at family gatherings. Oversized, overheated, and impossible to ignore. Far colder, far quieter, lies a planet discovered through microlensing. OGLE, 2005, BL390LB. The name doesn't charm the tongue, but its reality is remarkable. This world is frozen, locked far from its weak star. Surface temperatures hover near minus 220 degrees Celsius. And yet, models suggest that beneath its icy shell, tidal heating may keep a hidden ocean liquid. A frozen desert above, a secret sea below. That combination is powerful. Because if one frozen planet can hide an ocean, then many others can too. And there are countless red dwarfs in the galaxy, each with frozen companions. Each, perhaps, holding oceans in the dark. It reminds us that habitability isn't only about sunshine. Sometimes, it is about warmth from within, about hidden layers that shield life from a hostile universe. Then we turn to Uranus, a planet that refuses to behave. Most planets spin with axes tilted slightly, like Earth's 23 degrees. But Uranus is tipped almost completely on its side, about 98 degrees. It rolls around the sun like a ball, not a top. Why? The best guess is violence. Early in its history, Uranus may have been struck by a planet-sized object. The collision knocked it over, leaving it lopsided forever. The result is seasons unlike any other. Each pole spends decades in sunlight, then decades in darkness. Its atmosphere, strangely cold compared to its siblings, may still bear the scars of that ancient strike. Uranus is a reminder that the solar system is not orderly. It is scarred, tilted, bruised. Planets are not above being shoved, and sometimes they never recover. On Uranus and Neptune, winds reach astonishing speeds, up to 2,000 kilometers per hour, faster than the speed of sound on Earth, faster than jet planes. The air there is thin but unbroken, nothing to slow the streams, nothing to scatter them. So they howl endlessly, invisible rivers of atmosphere whipping across giant planets. Astronomers measure them by watching clouds drift, by tracking Doppler shifts in spectral lines. And the verdict was clear. These winds are real. The planets are not gentle giants, but storm worlds, hiding their fury behind calm blue faces. Stand on a floating platform there, and you would hear nothing, the air too thin for your ears. But you would see the clouds race faster than any storm on Earth. A silent violence, hidden in the calm. And then, stars that are not quite round. A Kerner, for example. Spin it fast enough, and a star bulges at its equator. A Kerner spins so quickly that it becomes oblate, wider across its waist than from pole to pole. Seen from afar, it glows brighter at its poles, dimmer at its middle, a cosmic egg more than a cosmic sphere. We tend to imagine stars as perfect circles, serene and balanced, but some, like a Kerner, remind us that perfection is an illusion. Rotation bends even suns, and what we call normal is only what we see most often. Time, on Earth, feels like a constant. 1 second follows another, each heartbeat keeping pace with the tick of a clock. But near a black hole, even time bends. Einstein's equations tell us that gravity is not just a force. It is the curve of space and time. The stronger the gravity, the deeper the curve. And close to the black hole, the curve is so steep that time itself slows. For someone orbiting at the edge of a black hole, hours might pass while elsewhere in the universe, centuries unfold. To them, time is steady. To the outside world, it drags like syrup. Go closer, and the effect grows stranger. At the horizon, that invisible line of no return, time for the falling traveler appears to freeze. To outside eyes, they never quite cross. But to the one falling, the plunge is swift, unstoppable, inevitable. Inside, the math changes again. Time no longer moves forward as a choice. It becomes a direction, like down. The singularity is not a place you can avoid. It is a point in time you must reach. Black holes do not just consume matter. They consume our very understanding of before and after. If black holes twist time, galaxies twist our sense of life itself. Galaxies are factories of stars, glowing with the birth and death of suns. but some galaxies stop. Take Max 2129 to 1, a giant elliptical galaxy 10 billion light-years away. It looks old, quiet, already done with its star-making, despite existing in the early universe. How can a galaxy so young be so dead? One answer is gas depletion. Stars are born from clouds of hydrogen, and when the gas is gone, the nursery closes. But Max 2129 to 1 seems to have shut down faster than models allow. Too fast, too early, as though someone simply flipped a switch. It's like finding a teenager who is already retired. No drive, no energy, no growth. Just a quiet glow, too soon. Galaxies like this remind us that the universe does not run on a single timeline. Some places age quickly, others slowly. Some burn bright, others dim before they ever should. And then there are patterns in the chaos. Astronomers once noticed a curious clustering of gamma-ray bursts, colossal explosions of energy from collapsing stars, stretched across billions of light years. Too many, too organized, forming what seemed to be a structure larger than anything cosmology allows. They called it the Great GRB Wall. If real, it would dwarf superclusters, violating the very principle that the universe should look uniform on the largest scales. Some think it is an illusion, a statistical fluke. Others suspect it is a real sign that matter arranges itself into shapes even grander than we imagined. Either way, the sight unsettled astronomers. The universe, meant to be smooth and even, might instead be stitched with hidden architecture, a cosmic quilt of walls and filaments, too vast for human intuition to hold. Not all anomalies are so enormous. Some belong to single stars, flung far from home. These are rogue stars. Unlike rogue planets, which drift quietly, rogue stars can blaze across intergalactic space at blistering speeds. Some are ejected by supernovae. Others are slingshot by black holes. Still others are pulled free during galactic collisions, thrown like sparks from crashing embers. Imagine watching a star, something that should anchor a system, command planets, racing alone between galaxies, trailing no family, no orbit, no home. Some travel fast enough to escape their galaxy entirely, vanishing into the dark between clusters. They become lonely lighthouses, reminders of violence long past. To them, the night is not filled with neighbors. It is only void. It is a strange role reversal. Stars, the anchors of order, reduced to drifters. And then there are quasars, not strange to their existence, but strange for their behavior. Quasars shine with the light of billions of suns, powered by supermassive black holes. But they flicker. They brighten and dim over days, months, years. For something so enormous, their variability is bizarre. It suggests that the heart of a quasar, the feeding disk of its black hole, is no larger than our solar system. Imagine that, a structure capable of outshining a galaxy, packed into a space smaller than the distance from Earth to Pluto. One of the most famous is 3C273 in Virgo, about 2.4 billion light-years away. Through a telescope, it looks like a star. In truth, it is a torrent of matter spiraling into annihilation, blazing so fiercely that it lights the cosmos across unimaginable distance. Quasars should not exist in such abundance, and yet they do, each one a paradox of scale. Too small to be so bright, too bright to be so small. Even whole clusters of galaxies can be drawn into mysteries. There is a gravitational anomaly we call the Great Attractor. When astronomers map the motion of galaxies around us, they notice a drift. Thousands of galaxies, including our own Milky Way, are sliding in the same direction, as though pulled by an unseen mass. The visible matter does not add up. Something invisible must lurk there, something vast, bending the paths of galaxies themselves. Perhaps dark matter, concentrated and hidden. perhaps something else. We cannot see it directly. The Milky Way's own disk blocks our view, but we feel its pull. It is like living in a boat and sensing a current beneath, unseen but undeniable, carrying the vessel downstream. The great attractor reminds us that even at the largest scales, we are not stationary. We are drifting, carried by tides older than our planet, stronger than our stars. Another signal comes from the skies in bursts of radio waves. These are the fast radio bursts, or FRBs. They last only milliseconds. Brief flashes of energy, picked up by radio telescopes. Some repeat. Others remain one-time mysteries. Their sources are elusive. Some may come from magnetars, neutron stars with magnetic fields, so strong they could erase data from a credit card from half the galaxy away. Others remain unknown. What makes FRBs unsettling is their sheer power. In that split second, some release more energy than the sun does in days, and they come from billions of light years away, crossing oceans of time to reach our antennas. Imagine standing in silence and hearing just once a knock at the door, then another months later, then silence again. That is what FRBs feel like, messages without language, origins without answers. Magnetars themselves deserve a pause. They are neutron stars, but exaggerated. Their magnetic fields are trillions of times stronger than Earth's, strong enough to distort atoms, to stretch them into thin threads. When magnetars shift or quake, their magnetic lines snap, releasing bursts of X-rays or gamma rays. Some flare so intensely they could blind detectors from across the galaxy. And yet they are rare. In our Milky Way, only about 30 have been found. They are short-lived, too, fading after tens of thousands of years, a blink on cosmic timescales. So each magnetar we see is a brief flicker, a warning flare from a star that once was, a reminder that even death in space can be violent. Collisions between galaxies are not accidents. They are the engines of growth. When two galaxies meet, their stars rarely crash. The distances are too great, but their gas clouds collide, their shapes warp, and tidal forces fling matter outward. Over time, they merge, forming new, larger galaxies. Many galaxies we see today are the children of countless mergers. Their shapes are scars. Elliptical galaxies, in particular, often show signs of ancient collisions, their smoothness hiding turbulent histories. It means that our Milky Way, too, is not as innocent as it seems. It has eaten smaller galaxies, folded their stars into its arms, and one day it will meet Andromeda, a slow dance lasting billions of years, ending in a new, larger galaxy, with the night sky remade forever. And among the oldest of stars, we find another puzzle, the Methuselah star, HD 140283 to be exact, a star so ancient, its age seems to rival that of the universe itself. Estimates once placed it older than the Big Bang, an absurd result that forced astronomers to refine their models. Even now, its age is pegged at around 14 billion years, almost as old as time itself. The Methuselah star carries the chemical fingerprints of an early cosmos, when heavy elements were scarce and hydrogen and helium dominated. Studying it is like holding a fossil from the dawn of everything. And yet, there it burns, quietly, modestly, outliving civilization, continents, species, planets. There are patterns so large that even galaxies become small details. One such is called the Great Wall. Not a wall of stone, but a wall of galaxies, superclusters stitched together, stretching across hundreds of millions of light years. It is one of the largest structures ever mapped. Stand back imagination, and the universe looks less like empty space, more like a cosmic sponge. Filaments of galaxies form the ridges, and the voids are the empty bubbles in between. The Great Wall is one of these ridges, so immense that the word structure almost fails. Its very existence troubles cosmologists. If too many such walls exist, the assumption that the universe is smooth on the largest scales begins to crack. The cosmological principle, the idea that matter is evenly distributed in the long run, becomes shaky. The Great Wall is either an exception or a hint that our models need rewriting. Either way, it is there, glowing faintly with billions of suns, defying simplicity. Beyond walls lies a stranger truth. Parts of the universe are already lost to us, because space itself expands, not just the things in it. Light from many galaxies will never reach us. They're already receding faster than light can carry their message. To us, they may as well not exist. The observable universe has a radius of about 46.5 billion light years. But that's just what we can see today. In practice, the horizon is shrinking. More galaxies slip beyond our reach each moment. Not because they vanish, but because the expansion of space carries them away forever. It's a strange thought. The universe is not getting smaller, but our access to it is. Like standing in the center of a growing crowd and watching the outermost people drift away, never to be spoken to again. One day, only our local group of galaxies will remain visible. Beyond that, silence. The rest of the universe will be hidden, unreachable, forgotten. We live in a rare era when the cosmos is still visible. Future eyes will not be so lucky. But even in this fleeting window, the universe continues to surprise. Consider the strange phenomenon of dark flow. When astronomers study the motion of galaxy clusters, they expected randomness to cancel out on large scales. Instead, they found entire regions drifting in the same direction, as though pulled by something beyond our horizon. Perhaps it is a gravitational tug of massive structures we cannot see outside our observable bubble. Perhaps it is a hint of physics beyond our grasp. Whatever the case, the dark flow suggests that the universe is tides, unseen currents dragging galaxies like leaves on a pond. It is both humbling and slightly unsettling. Even on scales of hundreds of millions of light years, the cosmos is not still. Collisions can reveal truths, too. One of the most striking examples is the Bullet Cluster. Here, two galaxy clusters smashed through one another. The visible gas, hot and glowing, collided and slowed down, but the bulk of the mass, the dark matter, sailed through unaffected. By mapping the gravitational lensing of background galaxies, astronomers could see where the mass truly was. And it wasn't where the light was. The Bullet Cluster is one of the clearest demonstrations that dark matter exists. We may not know its nature, but we can watch its shadow. It is mass without light, gravity without glow, a ghostly backbone of the cosmos. It reminds us of how much of the universe is invisible. The stars and galaxies we admire are only a small fraction. The rest is hidden, silent, but no less real. Now, picture something lonelier, a rogue planet. Planets are meant to orbit stars, held in their warmth. But many are flung out, cast away by gravitational scuffles. They drift through interstellar night, unbound, forever in darkness. Estimates suggest there could be more rogue planets than stars in our galaxy. Hundreds of billions, perhaps trillions, each one a frozen wanderer. Imagine standing on one. The sky would never brighten. There would be no sunrise, no sunset, only eternal night, with stars sharp and unblinking above. Your breath would frost instantly. The ground would be bitterly cold. And yet, under thick atmospheres or icy shells, some may still hide oceans. Life, if it exists there, would never know the concept of the sun. Rogue planets are cosmic orphans, and they remind us that not all worlds have homes. Even worlds with homes can suffer extremes. Some orbit on paths so elongated that they bake near their star, then freeze in deep space, over and over. During close approaches, tidal heating stretches them, twisting their crusts, stoking volcanoes. When they swing away, they plunge into frozen stillness. Their skies change chemistry, their clouds shift, their weather collapses and reforms. These extreme orbits may tear planets apart. In some systems, the debris from shattered worlds falls into the star, polluting its spectrum with heavy elements. Astronomers can see the fingerprints, faint traces of calcium, iron, magnesium, and starlight, proof of cannibalism. Even stars, it seems, can eat their children. But the universe also gives us geysers, fountains from hidden oceans. Return to Enceladus for a moment. Its plumes of water vapor and ice particles do more than intrigue. They give us samples. By flying through them, spacecraft can taste the chemistry of oceans hidden beneath kilometers of ice. Cassini found salts, organics, even signs of hydrothermal activity, all without drilling, all without touching the seafloor. The geysers are gifts, small leaks from a world that should be silent. They whisper a possibility, that life may brew in oceans no sunlight touches. That warmth and chemistry can be enough. That darkness is not the end. Even stars play tricks with time. Some rotate so rapidly that they bulge at the waist, appearing brighter at the poles, dimmer at the equator. Seen from one angle, they blaze. From another, they dim. Measuring them is like trying to weigh a dancer mid-spin. A Kerner is such a star, stretched and distorted. Not a sphere, but an oblate egg of fire. Proof that even suns can lose their shape if they spin with enough speed. And then there is Uranus, tipped on its side, rolling around the sun instead of spinning upright. Its strange tilt may be the scar of an ancient collision. Whatever the cause, it leaves the planet in decades-long seasons. A pole in sunlight for years, then plunge into night for just as long. Its atmosphere is oddly cold, its interior quiet, its winds ferocious. A planet out of step, forever tilted, forever strange. Neptune joins the oddness with winds faster than sound. Supersonic streams tear across its surface, invisible rivers in a sky of blue. If you could float there, you would see clouds racing faster than planes, faster than storms on Earth, silent in thin air. We think of these distant worlds as calm, but they are not. They are roaring giants. Storms disguise as serenity. The universe itself is a fabric of stories, stitched together from light, gas, dark matter, and dark energy. Some of its stitches we can see, others we only guess. It is not smooth. It is not simple. It is full of walls and voids, flows and pulls, flames and silence. Everywhere we look, something breaks the rules. Everywhere we listen, something whispers a new question. And still, the pace is steady. Stars form, stars die. Galaxies grow, galaxies fade. Time stretches, time slows. The universe rolls on, calm and vast. In the dark between galaxies, a few lights shine brighter than entire clusters of stars. These are quasars, powered by supermassive black holes devouring matter at their centers. We tend to think of black holes as invisible, silent consumers. But when enough matter falls inward, it creates an accretion disk so hot it blazes across space. The result is a beacon visible billions of light years away. One of the most famous quasars is 3C273 in the constellation Virgo. Through an ordinary telescope, it looks like a star, but its true nature is something far larger. It is a furnace of infalling matter, radiating across the spectrum. For a time, it was the brightest known object beyond our galaxy, its light carrying across 2.5 billion years of space and time. Quasars vary. Some brighten and dim in days, others in years. For something so vast, their changes seem absurdly fast. Imagine a city the size of continents, and the whole skyline flickers overnight. It tells us the heart of the action is compact, no larger than our solar system, yet able to outshine entire galaxies. A paradox, glowing quietly in the dark. On even larger scales, the universe pulls on us in subtle ways. There's a region of space astronomers called the Great Attractor. Galaxies, including our own Milky Way, seem to be moving toward it, as though drawn by a hidden gravity well. Yet, when we look, we cannot see clearly. The disk of our own galaxy blocks the view. We know something massive is there. Perhaps it is a cluster of galaxies, or a dense web of dark matter. Whatever it is, its influence is real. Tens of thousands of galaxies drift in its direction, carried by its pull. It is like a current beneath a boat, invisible but undeniable. We may not know the shape of the Great Attractor, but we feel its hand, the fast radio bursts. They arrive as sharp pulses, lasting only milliseconds. A burst, a silence, sometimes another burst weeks later. Some repeat, others do not. Some are strong, some faint. The energy they release in those brief instants can match days of output from our sun, and they come from billions of light years away. Their sources are still debated. Some point to magnetars, others to black holes, others to mechanisms we cannot yet imagine. What is striking is how sudden they are. Imagine sitting in silence, and for the briefest moment, a knock echoes at the door. Then nothing. Then another, perhaps years later. They are cosmic knocks without explanation. Magnetars themselves are another puzzle. Neutron stars with magnetic fields trillions of times stronger than Earth's. Their surfaces quake. Their fields snap, and the result is a flare of X-rays or gamma rays so intense it can be detected across a galaxy. They are rare. In our Milky Way, only a few dozen are known. Yet models suggest there may be thousands. Their lives are short by cosmic standards, tens of thousands of years, then they fade. So each magnetar we find is a temporary candle, burning too hot, too strange, too quickly. A reminder that not all remnants are quiet. Some shout before they vanish. Collisions tell their own stories. Galaxies grow by merging, swallowing smaller ones, weaving stars into new shapes. When galaxies meet, their stars usually pass by without colliding. The distances are too vast, but their gas clouds crash, compressing and igniting waves of new star formation. Their gravity twists their shapes, pulling long tidal tails across space. Our Milky Way has done this many times. We see the remnants and streams of stars orbiting through our halo, leftovers of galaxies long consumed. And one day, far ahead, the Milky Way will meet Andromeda. It will not be sudden, but a slow ballet, lasting billions of years. The night sky will fill with Andromeda's growing shape. Stars will stretch, swirl, merge. In the end, the two galaxies will become one, larger, rounder, quieter. Our sky will never look the same. But not all stars are young. Some are relics. The Methuselah star, HD 140283, carries an age that challenges our models. For years, its estimates place it older than the universe itself, an absurdity that forced refinements. Even now, it is among the oldest known, about 14 billion years, nearly as old as time itself. Its composition shows a fingerprint of an early cosmos, low in heavy elements, rich in hydrogen and helium. It is like a fossil, holding within the memory a universe before galaxies grew bright. And yet, it burns on, a quiet ember from the dawn, defying expectations with each flicker. Structures larger than any single star or galaxy remind us how vast the cosmos is. The Hercules, Corona Borealis Great Wall, is one of them, a colossal arrangement of galaxies and clusters stretching over 10 billion light years. Its scale defies our understanding. Such a structure should not exist under current cosmological models. Yet surveys reveal it, sprawling across maps like an endless scar. Perhaps it is a chance alignment. Perhaps it is real. Either way, it humbles us. The universe, we thought, would smooth itself out on large scales. Instead, it seems to have built monuments too vast for us to explain. And all the while, the expansion continues. More and more galaxies slip beyond our cosmic horizon, lost forever. We think of the universe as expanding into space. But really, space itself is stretching. That is why no speed limit is broken. Even as galaxies recede faster than light, they are not moving through space. Space itself is carrying them away. This means the observable universe is a temporary gift. Already, many galaxies are gone to us. Their light will never reach our telescopes. No matter how long we wait, they are lost beyond the curve. It is like standing on a shore watching ships sail out. Some go too far, and the sea itself grows wider between you. The ships are not coming back. The sky we see today is not permanent. In the far future, stars will fade, galaxies will quiet, and the cosmic web will thin. The night sky itself will change. And yet, we are here now, in the moment when quasars still blaze, when FRBs still knock, when the great attractor still tugs, when galaxies still glow. It is a fragile moment in the life of the cosmos, and it is ours. Some planets hold together for billions of years. Others do not. There are worlds so close to their stars that the heat begins to unmake them. Their rocky surfaces vaporize, their atmospheres stream away, and dust tails stretch behind them like smoke from a fading fire. One such world is KIC 1255754 Its orbit lasts only 16 hours. Each day is a year there. The star above is so hot, so near, that the planet is slowly being stripped to nothing. Astronomers notice it because the star's light dipped irregularly, not like a normal transit. The dips varied, as though something dusty and shifting passed in front. That dust, it turns out, was the planet itself, evaporating, crumbling, leaving pieces behind. Every orbit, a little more is lost. Someday, perhaps not long on cosmic scales, there will be nothing left but the memory of a planet that could not survive its own sun. It is a strange fate. Worlds are meant to be solid, enduring, stable. And here is one dissolving in real time, a cosmic candle melting away. Others are stranger still, not dying, but erupting. On Saturn's tiny moon Enceladus, fountains burst from the South Pole. Geysers of water vapor and ice grains shoot hundreds of kilometers into space. When the Cassini spacecraft flew through them, it found salt organics, traces of heat, signs of a global ocean beneath the ice, warmed by Saturn's tidal pull. That ocean is sealed under kilometers of ice, but the geysers bring its secrets into the open. They are like messages written in spray, telling us what lies below without forcing us to dig. Enceladus is small. It should be frozen solid. But somehow it is alive with motion. Its plumes whisper that even tiny worlds can hold oceans and perhaps something more. Not all skies shine with one sun. Some worlds orbit two stars. Kepler 16b is one of them. From its surface, if you could stand there, you would see two suns rising and setting, sometimes together, sometimes apart. Shadows would overlap, stretch, and twist in ways no earthly sunset could show. The world itself is cold and gaseous, unlikely to host life. But its sky is the stuff of imagination, a constant dance of light, red and gold, weaving across days and seasons. We grew up thinking one sun was normal, but in truth, many stars are binaries. The universe seems to prefer pairs. Planets like Kepler 16b remind us that Earth's sky is only one version of what's possible. Some worlds go further, rejecting light entirely. Trace 2b is a planet darker than coal, darker than fresh asphalt. It reflects less than 1% of the light that strikes it. Why? Its atmosphere is thick with chemicals, sodium, potassium, titanium oxide, that swallow light whole. From afar, it appears almost invisible, glowing only faintly with its own heat. Imagine passing by in a spacecraft. You would not see a shining orb, but a black sphere, outlined only by the glow of its nearby star. A planet made of absence, drifting silently. It is the closest thing in nature to a hole that is not a hole. Not a black hole, but a black world. Not all stars accept their fates quietly. Some white dwarfs, the dense cores of dead stars, orbit companions. They pull gas from their neighbors, hoarding it on their surfaces. Eventually, the gas ignites in a flash. A nova. For some, this repeats. Outbursts again and again as the white dwarf feeds and flares. These are recurrent novae, cosmic heartbeats of fire. Each eruption blasts heavy elements into space, enriching the galaxy with new materials. Iron, carbon, oxygen scatter like seeds. Stars die, but in dying they give. Even their theft becomes creation. Gas giants can play their own chaotic games. Hot Jupiters, swollen by heat, often drift inward from where they formed. In doing so, they destabilize their neighborhoods, flinging smaller planets away or pushing them into their stars. This may be why hot Jupiter systems often lack rocky companions. The giant has cleared the table, leaving itself alone beside the fire, inflated, oversized, sometimes with atmospheres twice the radius of Jupiter. They are bullies, but also fragile, puffed up by their stars, doomed to evaporate over time. Showy, loud, and short-lived. Far away, a frozen planet carries another lesson. Jelly, 2005, BLG 390LB. A name without music, but a world with secrets. Its surface is frozen at 200 degrees below zero. Yet models suggest that beneath its icy shell, tidal heat may sustain a hidden ocean. A frozen crust above, liquid water below. Not one world, but many could be like this. Red dwarfs, the most common stars, may host swarms of such icy companions. It widens the definition of habitable. Life may not need warmth from a sun. It may only need an ocean and a little heat within. Closer to home, Uranus continues to puzzle. Tilted almost completely on its side, it rolls around the sun like a ball instead of spinning like a top. Its seasons are bizarre. Poles baked in sunlight for decades, then locked in darkness for just as long. Its interior is cold compared to Neptune. Its winds are fast, its history scarred. Perhaps a colossal impact tipped it. Perhaps more than one. Whatever the reason, Uranus refuses to align with the rest. A reminder that even in our solar system, normal is an illusion. Neptune, too, hides storms. Its winds reach supersonic speeds, tearing across the blue atmosphere faster than sound. Clouds race faster than jet planes, faster than anything Earth has ever known. From a distance, Neptune looks serene. But up close, it is a world of motion, roaring in silence, storms forever unending. The giants teach us that appearances deceive. Calm blue is only a mask. Even stars lose their roundness. Spin them fast enough, and they bulge at the equator. A Kerner is such a star. Its equator stretches wide. Its poles remain hot and bright. From one angle, it glows intensely. From another, it dims. We imagine suns as perfect spheres. A Kerner is proof they are not. Rotation bends them, reshapes them, warps their light. Perfection is rare. Even stars wobble. And so, the universe keeps handing us contradictions. Worlds that vanish, moons that erupt, planets that float in double sunsets, stars that refuse to stay round. We expected order. What we found is variety, and that variety is endless. Time bends near black holes. We know this now, measured in the equations of relativity, seen in the shifts of light. As you drift closer to the event horizon, clocks outside tick faster. Your seconds stretch into years. It is not imagination. It is math, written in the shape of space-time itself. Time slows as gravity deepens. To you, life feels normal. To an observer far away, you are caught in molasses, slowing until you appear frozen at the edge of forever. It is one of the strangest truths. Time is not universal. It is personal, shaped by where you are and how strong gravity pulls. Even the most basic rhythm of existence is negotiable. Black holes are not only prisons of matter, they are prisons of time. Galaxies, too, face strange fates. Some burn themselves out early, like candles flaring too fast. One such galaxy, max 2,129 to 1, lies 10 billion light years away. By rights, it should still be forming stars, but it is already dead. A compact core of old suns, no fresh hydrogen, no nurseries of light. It is as though it aged ahead of schedule, skipping youth and middle age to collapse directly into quiet old age. Astronomers call such galaxies quenched, a polite word for cosmic burnout. It raises questions. Why did it stop so soon? Did it exhaust its gas? Was it stripped by neighbors? Or do we misunderstand the rhythm of galactic life entirely? The answers remain cloudy. But the image lingers, a galaxy that grew tired long before its time. Even more puzzling are the vast alignments of energy. Astronomers once charted a curious clustering of gamma-ray bursts, those colossal explosions that follow the collapse of massive stars. Instead of scattering randomly across the sky, many seem to line up, forming an enormous ribbon. They named it the Hercules Corona Borealis Great Wall, a structure so large, 10 billion light years across, that it defies cosmology. The universe is not supposed to build such monuments. Some argue it's an illusion, a statistical accident, an artifact of observation. Others say it is real, a scar creation itself. Either way, it humbles. For if the wall is real, then our models of uniformity crumble. The universe is less even, less simple, more sculpted than we believed. And yet, in this immensity, single stars can tell stories too. Some are cast out of their galaxies entirely. These are the rogue stars. Unlike planets, which drift quietly, rogue stars blaze alone. They are exiles, flung by gravitational encounters. Perhaps two supermassive black holes fought for dominance, and a star was thrown aside as collateral. Perhaps a galaxy merger twisted orbits until some were cast away. Now they race across intergalactic space, lonely beacons in the void. Some may carry planets with them, whole systems exiled together, drifting where no galaxy waits. A strange inversion. The very objects meant to anchor systems reduced to wanderers. Others remain anchored, but burn with absurd fury. Quasars, we've seen them, blaze brighter than entire galaxies, powered by black holes devouring at their centers. Their flickering is strange enough, but stranger still is their compactness. All that light, all that energy, compressed into a region smaller than the span of our solar system. It is a paradox the universe seems fond of, the brightest things born from the darkest hearts. The universe's other hidden poles. 2. Galaxies around us drift toward a mysterious region we cannot see, known as the Great Attractor. Tens of thousands of galaxies, ours included, move in that direction at hundreds of kilometers per second. Yet our own Milky Way blocks the view with its dust and stars. We cannot see the source directly. What lurks there? A supercluster? A massive web of dark matter? Or something else entirely? We don't know, but the pull is there. A current we cannot resist, carrying us into the future. And while galaxies drift, signals flicker. Fast radio bursts, FRBs, are among the strangest. Sudden flashes of radio energy, lasting milliseconds, brighter than whole galaxies in that moment. Some repeat. Some do not. Some come in clusters, others alone. Their origins remain uncertain. Magnetars may explain a few, but others defy neat boxes. Imagine sitting in the silence of a radio telescope. For hours, only static. Then, a pop, a spike, a voice with no words, from billions of light years away. Then nothing again. They are the universe's knock on the door. Brief, startling, unanswered. Magnetars themselves are worth pausing on. They are neutron stars, collapsed remnants of supernovae, but with magnetic fields so extreme they distort atoms. If one sat as far away as the moon, its field would erase every credit card on Earth. When those fields snap, the release is violent. Gamma ray flares bright enough to travel across a galaxy. They are rare, short-lived, unstable. Yet in their brief lives, they shout louder than most stars do in billions of years. A cosmic irony. The loudest voices belong to the shortest lives. On the grandest scales, galaxies grow not alone, but together. Collisions are common, even essential. When two galaxies meet, stars rarely collide, but gas clouds smash and ignite bursts of star formation. Shapes twist, spiral arms stretch, tails of stars fling outward. The universe builds new by breaking old. Our Milky Way, too, has consumed smaller galaxies, weaving their stars into our halo. And one day, we will merge with Andromeda. The sky will fill with its stars. Over billions of years, the two galaxies will dance, merge, and settle into one. Even destruction can be creation. And among the oldest stars, we find the quiet witnesses. The Methuselah star, HD 140283, carries an age so great it nearly rivals a universe. A fossil of hydrogen and helium, with barely a trace of heavier elements. It burns still, though dimly, as if holding the memory of a younger cosmos. A reminder that time, though vast, is not endless. Even the oldest star will one day fade. The universe builds walls of galaxies, sends stars into exile, lights quasars with fury, and lets magnetars scream across silence. It is chaotic, yes, but it is also patterned, layered, stitched together. Everywhere we look, something breaks the rules. And everywhere, something insists, rules are only guesses. The universe is not endless in what we can see. Already, galaxies slip beyond our reach. We are used to thinking of distance as a matter of speed. Drive faster, fly faster, and eventually you'll get there. But the cosmos doesn't play by that rule. Space itself expands. And because of that, some galaxies are receding faster than light. Their signals will never arrive. We live inside a shrinking bubble. Today it is vast, 46.5 billion light years in radius. But that is only what light has had time to show us. Beyond that, most of the universe is already gone to us. Not destroyed, simply unreachable. It is as though you stand on a shoreline, and each wave carries more ships beyond the horizon, never to return. One by one, the lights fade. In the far future, the night sky will be empty. Our descendants, if they exist, may believe the cosmos ends with their own galaxy. They will never know the truth, that once there were billions of galaxies, glittering like fireflies, drifting outward into silence. We live in a rare era when the stars still tell their story. This expansion is driven by dark energy. It is not matter. It is not light. It is a property of space itself. The more space expands, the more dark energy fills it. The more dark energy fills it, the faster space expands. A feedback loop with no end. Gravity still wins locally. Stars form. Planets orbit. Galaxies cluster. But on larger scales, dark energy dominates. It stretches everything wider, faster, further. The result is a universe that grows lonely. Islands of galaxies separated by oceans of emptiness, each drifting further apart. It is a quiet kind of apocalypse. Not a sudden fire, not a violent collapse. Just a slow, unstoppable widening until all is alone. On smaller scales, stars continue their own cycles of drama. Some, like recurrent novae, flare again and again, stealing from their neighbors, burning in bursts. Others, like magnetars, flash for mere moments in cosmic history before fading. Even the most ordinary stars have their strangeness. Our own sun will swell into a red giant, engulfing Mercury and Venus, perhaps even Earth. Then it will shed its outer layers, leaving behind a white dwarf. Billions of years later, that white dwarf will cool, crystallize, and become like Lucy, a diamond star, cold, silent, and enduring. So the fate of our sun is to become a jewel. A fitting end for the light that once grew forests, built oceans, and warmed our nights. Other stars died differently. Some collapsed into neutron stars, city-sized spheres heavier than mountains. Some into black holes, twisting time and space into singularities. The universe is full of corpses, but they're not lifeless. Neutron stars still spin, pulsars still beam, white dwarfs still glow. Black holes still shape the world around them. Death in space is not an end. It is a transformation. Even galaxies, the grandest structures, have their own mortality. Spirals like the Milky Way are sustained by gas clouds, by steady star formation. But once the gas runs out, the stars fade, and no new light replaces them. The galaxy becomes elliptical, smooth, dim, a graveyard of ancient suns. Billions of years ahead, most galaxies will be this way. Quieter, older, less vibrant, still vast but subdued. The universe will grow pale, like a painting left too long in sunlight. Yet even in this fading, new mysteries appear. We've seen galaxies colliding, stars flung into a galactic dark, rogue planets drifting without suns. We've seen structures larger than thought possible, voids emptier than intuition allows. We found stars older than model predicted, black holes larger than theories explained, planets stranger than imaginations had drawn. The universe, it seems, enjoys breaking its own rules. And beyond the farthest galaxies, there is still more, perhaps other universes, perhaps nothing, perhaps answers, perhaps silence. Our tools are small. Our lifespans are short. Yet here we are, listening, measuring, wondering. There is something quietly comic about it. Fragile beings of flesh, peering into infinite dark, try to write rules for eternity, as though ants were sketching blueprints for mountains. And yet, against the odds, some of those sketches work. It is both humbling and comforting. We are small, but we can see far. In the end, the universe will not rage. It will fade. Stars will die. Galaxies will quiet. Black holes will evaporate. What remains is not fire, but silence, a deep, cold equilibrium, where time stretches but little changes. It is not the ending of a story, but the settling of a long breath. And here we are, now, in the brief window when stars still blaze, when galaxies still shine, when light still reaches us from the beginning. We can look and measure and wonder. We can tell stories of diamond stars, boiling worlds, twin sunsets, black holes larger than imagination, and structures vaster than reason. Things that should not exist, but do. Stars are not always what they seem. Some, when they collapse, leave behind secrets hidden in their cores. Neutron stars, for instance, are already absurd. A city-sized ball holding more mass than the sun. But within them, the density may go deeper still. Some theories suggest quark stars, where even neutrons break apart, dissolving into their constituent quarks. If true, they would be matter stripped to its simplest building blocks. We have hints. Pulses and flares that resist ordinary explanation, objects too dense to be neutron stars, yet too small to be black holes. Candidates for something in between. If they exist, quark stars are rarer than rare, quiet anomalies in a universe that delights in extremes. Other stars refuse to behave quietly. They beat, flare, and burst without warning. Among them are the repeating giant of high-energy astronomy, strange objects called soft gamma repeaters and anomalous X-ray pulsars. For years, scientists thought they were different species. In truth, they are both magnetars, showing different faces of the same strange being. When magnetic fields snap, the bursts follow. They can rattle detectors across light years, leaving behind echoes that linger in radio and X-ray bands. It is as though the star hiccups, and the galaxy notices. The cosmos offers another kind of burst, the fast radio burst. So brief it lasts only a millisecond, yet so bright it can outshine a galaxy in that instant. Some repeat regularly, like cosmic lighthouses flashing in rhythms we have not yet decoded. Others remain stubbornly silent after their first shout. We have cataloged hundreds now. Some bursts come minutes apart, some months, some years. Each carries energy across billions of light years, whispering a story we still cannot read. Perhaps they are magnetars, perhaps black holes, perhaps something stranger. For now, they remain knocks on the cosmic door, with no one yet opening it. Galaxies themselves write bursts into their history. When two galaxies merge, the violence triggers waves of star formation, lighting whole regions with newborn suns. Streams of stars are thrown outward, long tails curling like ribbons. Our Milky Way has done this, too. We see the remnants, faint arcs of stars looping around us, leftovers from galaxies long consumed. And one day, we will merge with Andromeda. Slowly, over billions of years, the night sky will swell with its shape. Stars will scatter and settle. In the end, the two will become one, a giant elliptical, calmer, quieter, but rich with the ghosts of its past. Even destruction, on these scales, is creation, and still, some stars predate even galaxies. Among the oldest known is HD 140283, the Methuselah star. Its age nearly rivals the universe itself, 14 billion years. It is low in heavy elements, rich in primordial hydrogen, and helium forged in the Big Bang. It shines still modestly, a survivor from a time before the Milky Way was fully formed. Looking at it is like looking back in time, not to an age of galaxies, but to an era when the first stars flickered awake. It is a quiet reminder. The universe remembers its beginnings, but the universe also builds structures too vast to comprehend. The Hercules, Corona Borealis Great Wall, is one of them, a chain of galaxies in clusters stretching across 10 billion light years. Our models of cosmology strain under its weight. No structure should be that large. And yet, surveys reveal it, a cosmic wall, too vast for metaphor. Perhaps it is a statistical illusion. Perhaps it is real. Either way, it forces us to question the neatness of our maps. The universe, we thought, smoothed itself out at the largest scales. Instead, it has built monuments beyond imagination. Beyond walls lie voids, spaces so empty they seem unreal. These cosmic voids are not black holes, not negative matter, just emptiness. Regions hundreds of millions of light years across, with barely a galaxy inside. We can map them by their effects, the way galaxies bend around their edges, the way light curves as it passes. They are invisible craters in the cosmic fabric, holes not of substance but of absence. Stand in one, and the sky within. Galaxies would cluster on the distant horizon, leaving you in a silence deeper than silence. The voids remind us that emptiness is as much a part of the universe as matter. Close at home, we see other extremes. Planets too light for their size, like Kepler 51b, a gas giant swollen into a fluffy ball with the density of cotton candy. So light, it could float in water. Planets too dark, like Trace 2b, reflecting almost nothing, hiding in plain sight. Moons too active, like Enceladus, erupting geysers from oceans no sun warms. Everywhere, exceptions. Everywhere, reminders that normal is only what we are used to. The universe does not apologize for its contradictions. It holds diamond stars and boiling planets, moons with seas of methane, and planets with skies of glass, galaxies without dark matter, and black holes so large they should not exist. It is, in every corner, stranger than imagination, and yet in its strangeness it is steady. Stars form, stars die. Galaxies merge, galaxies fade. Planets evaporate, moons erupt, black holes spin. A rhythm too slow for human eyes, but constant all the same. The night sky we see today is not forever. Every star above you, every galaxy, every faint smudge of light, all of them are temporary companions. Already, galaxies slip beyond our horizon, not because they vanish, but because space itself expands faster than their light can reach us. One by one, they fade from view. In trillions of years, the sky will hold only our own local group. The Milky Way, Andromeda, and their smaller companions merge into a single swollen galaxy. Beyond that, nothing. Future astronomers will look out and see emptiness, believing they are alone. They will not know of the countless galaxies that once filled the dark. They will not know of cosmic expansion or the Big Bang or the vast web of matter. They will live in a universe that hides its past. We, today, are in a rare moment, a moment when the light still reaches us, a moment when the universe still speaks. But even our local stars will fade. The brightest suns burn the fastest. Blue giants, massive and hot, live only millions of years. Then they collapse, explode, or leave behind black holes. Our sun, more modest, will last about 10 billion years. Halfway through its life already, it will swell into a red giant, shedding its outer layers, burning brighter, then fading into a white dwarf. The white dwarf will glow dimly, cooling over billions of years, until it becomes a black dwarf, cold, invisible, silent. Other stars will follow. One by one, the skies will dim. Galaxies will lose their shimmer. The night will grow sparse. It is a long process, far beyond human scale. But it will happen as surely as dawn follows night. And what of the giants? Some stars collapse into neutron stars, city-sized, but heavier than the sun. They spin, beam, pulse, hum across the cosmos. But even they slow. Their energy leaks away. Their light fades. Some collapse further into black holes, invisible pits of gravity, swallowing all that drifts too close. Black holes can endure longer than stars, longer than galaxies. But even they are not eternal. According to theory, black holes evaporate slowly through a process called Hawking radiation. For small ones, it is fast. For the giant ones, it takes longer than the universe has yet lived, trillions upon trillions of years. But eventually, even the most massive will fade, leaving behind nothing but faint heat. Even the monsters are temporary. Between these slow endings, the universe will pass through eras. First, the stelliferous era, the age of stars which we live in now. Light fills the sky, galaxies blaze, planets orbit warmth. Later, the degenerate era, when stars are gone and only remnants remain. White dwarfs, neutron stars, black holes. The sky will be darker, colder, quieter. Further still, the black hole era, when black holes dominate, swallowing the last matter, holding the last sparks of energy. And finally, the dark era, When even black holes are gone, when the universe is filled with nothing but thin particles drifting endlessly, the eras stretch beyond imagination. But they remind us that time does not end with us. The universe has chapters we will never read. Even in these futures, strangeness may continue. Rogue planets drifting alone, moons hiding oceans beneath ice, collisions still happening, black holes still merging. But the overall trend is clear. The universe will dim, light will fade, entropy will spread. It is not a fiery end, but a quiet one. The cosmos will not collapse nor explode, but simply cool, widen, and fade. There is a strange comfort in that. The universe began with violence, the Big Bang, expansion, fire. It has been loud with supernovae, quasars, collisions. But its end is gentle, not with a bang, but with silence. And yet, within this silence, there will still be motion. Protons may decay, or perhaps not. Photons will stretch, wavelengths growing longer, energy thinning. Time will continue, but events will become rarer, then rarer still. Eventually, the universe will be so empty that nothing changes. Trillions upon trillions of years, each indistinguishable from the last. A universe not of stories, but of stillness. From here, looking forward, the contrast is sharp. We live in abundance. Stars shining, galaxies spinning, light traveling across billions of years. We live in noise and brightness, compared to what will come. And so, our moment is special. Our sky is full. Our telescopes reach far. Our models can glimpse the past. We live in the universe's middle age, when it is neither too young nor too old. It is the best time to ask questions, the best time to wonder, the best time to listen. And the universe, in its odd way, answers. With diamond stars, boiling planets, moons of methane lakes, worlds of glass rain. With galaxies without dark matter, with pulsars spinning hundreds of times a second, with black holes bigger than models allow. It answers by breaking rules, by creating things that shouldn't exist, and placing them calmly in the sky. It reminds us that the word impossible is small, that the cosmos does not care for our expectations, that its creativity is wider than ours. Gravity is our anchor. It holds our feet to the ground, keeps the moon in orbit, binds Earth to the sun, and the sun to the Milky Way. It is the great invisible tether that keeps the cosmos stitched together. But at the scale of galaxies, gravity plays tricks. We see stars spinning around the centers of galaxies too fast. If gravity were only the pull of visible matter, they would fly apart, scatter like sparks from a fire. Yet they hold. To explain this, scientists propose dark matter, an invisible substance that outweighs ordinary matter 5 to 1. It does not shine, does not absorb, does not interact except through gravity. It is the hidden skeleton of galaxies. And yet, we found galaxies without it. Places where stars move as though no invisible glue holds them. Galaxies that should not exist, but do. If those galaxies are real, they may suggest something radical. Perhaps gravity itself behaves differently on these scales. One idea is modified Newtonian dynamics, or MOND, a theory that tweaks the law of gravity at low accelerations. Most physicists prefer dark matter. MOND is controversial, difficult to reconcile with other observations. And yet, the galaxies without dark matter persist, like pranksters reminding us that our equations are not sacred. It is humbling to think that one of the most fundamental forces may still hold secrets, that the same pull that drops an apple might twist in unknown ways among the stars. The cosmos loves these quiet puzzles. Sometimes it hides them in vastness, other times in silence. Consider the cosmic microwave background, the faint afterglow of the Big Bang, a whisper of heat left from when the universe was only 380,000 years old. It is everywhere, in every direction, a nearly uniform haze of microwave light. Nearly uniform, because hidden in that smoothness are tiny fluctuations, patterns so faint they took satellites to reveal. Yet those ripples are the fingerprints of the first structures, the seeds of galaxies and clusters. From silence, complexity grew. From smoothness, structure bloomed. It is strange to think that all the galaxies, all the stars, all the worlds began as whispers in that faint glow. But not all whispers are faint. Some come as sudden cracks across the cosmic silence, gamma ray bursts. These explosions release more energy in seconds than the sun will in its entire lifetime. Some come from collapsing stars, others from merging neutron stars. They should be rare. And yet, when astronomers mapped them, they found alignments, too many bursts clustering along vast arcs. Perhaps chance. Perhaps a new kind of structure, vaster than cosmology allows. We call them walls, filaments, alignments, words too small for their scale. The truth is, the universe may not be smooth. It may be lumpy and stretched, patterned in ways we cannot yet imagine. Stars themselves show their own quiet strangeness. Some burn out of sync with their age. Some pulse irregularly, like hearts missing beats. Some spin so fast they flatten, glowing brighter at their poles, dimmer at their wastes. And then there are the pulsars, neutron stars, rotating hundreds of times per second, beaming radio waves like lighthouses. Their precision is astonishing. Some keep time better than atomic clocks. Yet others stutter, glitch, shift suddenly in speed. They are machines built by collapse, but they are not perfect. They remind us that even the universe's most regular metronomes can falter. Beyond the stars, entire galaxies behave strangely. Some simply stop making new stars, long before their gas should run out. They are called quenched galaxies. Perhaps they lost their gas in violent encounters. Perhaps feedback from black holes heated their clouds too much for collapse. Whatever the cause, they sit as silent embers, already age a young universe. It is as though they decided prematurely that they were done with creation. Cosmic teenagers that retired too early. The patterns extend to motion. Whole groups of galaxies drift in the same direction, pulled by something unseen. Astronomers call it dark flow. It should not exist. Motions on such scales should cancel out, smoothing across billions of light years. And yet, the drift continues, as though a hidden hand tugs from beyond our observable horizon. What lies there? More mass unseen? Or something deeper, a hint of structures in universes beyond our own? We cannot know. We can only measure the pull and admit we are not standing still. Closer to us, we find orphan worlds, rogue planets, set adrift after being ejected from their systems. They wander without suns, frozen and lonely, yet possibly harboring warmth deep inside. Thick atmospheres may trap heat. Tidal forces may stir hidden oceans. If life exists on such worlds, it would never see a sky change. No sunrise, no sunset. Only endless night, broken by stars too distant to warm. Perhaps life does not need dawn. Perhaps persistence is enough. The universe offers one more irony. As stars fade, as galaxies grow quiet, as black holes evaporate, the cosmos will settle into stillness. But the laws of physics, as far as we know, will continue. Gravity will still curve space-time. Quantum fields will still hum faintly. Particles will still dance, even if slowly. It means the universe may never end. It may simply stretch into a silence so vast that nothing ever breaks it. Not destruction, but stillness. And in that stillness, every strange thing we have seen, diamond stars, boiling planets, rogue wanderers, bursting gamma rays, tilted giants, will be memories written in the dark. The universe builds by colliding. Galaxies meet, merge, and reshape one another. Stars within them rarely touch, The distances are too great, but the gas clouds do. When they crash, new stars are born in sudden waves, filling regions with newborn light. These encounters are not accidents. They are the natural rhythm of the cosmos. Over time, small galaxies fall into larger ones, streams of stars stretching like rivers across the sky. The Milky Way carries such streams still, remnants of ancient galaxies it consumed long ago. Our own future is written in this rhythm. In about 4 billion years, the Milky Way and Andromeda will collide. It will not be quick. For billions of years, their arms will twist and tear. Their cores will pass through one another, their stars flung into long tidal tails. From Earth, if Earth survives, the sky will bloom with Andromeda's growing shape, first as a faint smear, then as a grand swirl, then as a chaos of stars. In the end, the two galaxies will settle into one, a massive elliptical, quieter, older, carrying within it the memories of both. Even destruction in space is a kind of creation. Stars, too, collide. When two neutron stars spiral into each other, their merger is violent. Gravitational waves ripple through space-time, shaking the fabric of reality itself. Bursts of gamma rays shoot outward, and in that violence, something rare is forged. Heavy elements, gold, platinum, uranium, materials we prize on Earth, are born in those collisions. The rings on our fingers, the circuits in our machines, the coins in our pockets all trace back to a moment when two dead stars slammed together in silence. It is a strange thought that jewelry and technology carry the memory of stellar death, that what we call wealth was born in catastrophe. Some stars collapse instead of colliding. Massive ones implode into neutron stars or black holes. But sometimes they take a stranger route. Their collapse triggers an explosion, not a supernova, but something fiercer, shorter, sharper, a gamma ray burst. These bursts are the most powerful explosions we know, visible across billions of light years. They should be rare, yet our sky holds many records of them. Some arrive without warning, lasting seconds, then gone. Others linger longer, minutes, hours, slowly fading. The afterglows tell us what happened. Collapsing cores, merging stars, the death of giants. The bursts themselves remind us that the universe can speak suddenly, loudly, and without warning. Some stars, after collapse, do not go quietly. They spin. These are the pulsars, neutron stars rotating hundreds of times per second. Their magnetic fields sweep beams of radiation across space, like lighthouses. To us, the beams blink steadily, rhythm so precise they rival atomic clocks. Yet even pulsars falter. Some glitch, suddenly changing speed, as though something inside cracked. Others slow over time, their energy leaking away into space. They are clocks built by catastrophe, ticking in the dark. But even clocks wear down. Then there are the magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. When those fields snap, the energy release is staggering. Bursts of X-rays and gamma rays flare across galaxies. Some magnetars release more energy in seconds than the sun does in 100,000 years. Yet they are fleeting, rare, short-lived. In a galaxy of hundreds of billions of stars, only a handful become magnetars, and their lifetimes are measured not in billions, but in tens of thousands of years. They are firecrackers compared to the slow burn of stars. Brief, violent, unforgettable. Even when stars die quietly, they leave puzzles. White dwarfs, for instance, sometimes sit in binary systems, stealing gas from their companions. The gas builds until it ignites, triggering a nova. Some do this again and again, recurrent novae, flaring like clockwork. Others gather so much matter that they cross a threshold, collapsing entirely into neutron stars or black holes. The process scatters heavy elements into space, enriching the next generation of stars. It is recycling at cosmic scale. Death feeding life, ashes seeding futures. Galaxies hold their own mysteries. Some stop forming stars altogether, long before their gas runs out. They are called quenched galaxies, dim embers in the cosmic night. Why they quench so early is not always clear. Feedback from black holes may heat their gas, preventing collapse, or encounters may strip their raw material away. Whatever the reason, they sit like retired factories, glowing faintly, creating nothing new, silent, patient, faded. Others stretch the definition of structure itself. We map the universe in filaments and walls, superclusters, and voids. One of the most striking is the Great Wall, hundreds of millions of light years across. Another is the Hercules Corona Borealis Great Wall, spanning 10 billion. These structures test the limits of cosmology. They should not exist, not at such scales. And yet, our surveys reveal them. They remind us that the universe is not smooth. It is clumped, lumpy, webbed together by gravity. At human scale, a wall is a structure you can touch. At cosmic scale, a wall is something you cannot comprehend, only trace with light. And then the voids, great regions of almost nothing, stretching for hundreds of millions of light years. Not black holes, not dark energy, just emptiness. They are not truly empty. A few galaxies drift through them, but compared to the crowded filaments, they are deserts. Stand in one, and the horizon within. Galaxies would cluster faintly at the edges, leaving the center vast and bare. Voids are as much a part of the universe as walls. Silence balances sound. Emptiness balances light. All of this, walls, voids, galaxies, stars, drifts within the slow expansion of space. The observable universe shrinks in practice, as more galaxies slip beyond reach. We live in a moment when the sky is still crowded, when telescopes can still see billions of years into the past. One day, even that view will be gone. For now, though, the sky is full, and in its fullness, we see things that shouldn't exist, but do. Every star has a lifespan. Some end quickly in millions of years. Others linger for billions, but none last forever. The most massive stars burn the brightest and die the fastest. Their lives are brief, burning through their fuel until they collapse in catastrophic supernovae. Their deaths scatter heavy elements into space, seeding future generations of stars and planets. Our sun is quieter. It has lived for 4.6 billion years and has about 5 billion more to go. One day, it will swell into a red giant, engulfing Mercury, Venus, and perhaps even Earth. Then it will shed its outer layers, leaving behind a white dwarf, a small, dense ember glowing faintly. Over time, that ember will cool, its heat leaking away into space. Billions of years later, it will crystallize into a diamond-like sphere, a black dwarf. Silent, dark, unchanging. The fate of the sun is not fire, but stillness. Other stars follow stranger paths. Some collapse into neutron stars, only about 20 kilometers wide, yet heavier than the sun. On their surfaces, a teaspoon of matter will weigh billions of tons. They spin, pulse, beam radiation like lighthouses. Over time, they slow, dim, and fade. Some collapse even further into black holes, invisible pits of gravity, so dense that nothing, not even light, escapes. For now, black holes seem eternal, but theory says they are not. They should evaporate, slowly, through Hawking radiation. For stellar black holes, the process takes longer than the current age of the universe. For giants like TON 618, it takes unimaginably longer. But in the end, even black holes will fade, dissolving into faint heat. The most massive objects in the cosmos are only temporary guests. The universe will not end in a blaze. It will end in silence. First comes the stelliferous era, our current age, filled with stars and galaxies. Then comes a degenerate era, when star formation ends, when only remnants remain, white dwarfs, neutron stars, and black holes. Then the black hole era, when black holes dominate, swallowing the last matter, merging, colliding, slowly evaporating. Finally, the dark era, when nothing is left but thin radiation, weak particles, and silence stretched across eternity. These eras span trillions of years. They are not for us to see, but they remind us of the scale of time, compared to which human history is less than a spark. Even before those distant futures, the universe gives us glimpses of endings. Some stars already flare, burst, and vanish in moments. Gamma ray bursts tell us of massive stars collapsing. Supernovae scatter elements across galaxies. Magnetars erupt with bursts of radiation. The sky is not static. It is alive, restless, burning and fading all at once. If we could speed up time, we would see stars pop like fireworks, galaxies collide like waves, clusters drift like clouds. Instead, we see only stillness, unaware of the storm beneath. Galaxies themselves evolve. Spirals like the Milky Way burn brightly, forming new stars from hydrogen gas. But eventually, that gas runs out. The spirals fade, leaving only older stars. They become elliptical, smooth, dim, quiet. The great engines of star formation stall. The universe shifts from birth to memory. One day, nearly all galaxies will be like this. Silent cities of old stars, glowing faintly, with no new generations to follow. Even stranger are the rogue worlds. Ejected from their systems, they drift alone in darkness. No star to orbit, no light to warm them. And yet, they may hold heat inside, trapped beneath ice or atmospheres. Perhaps oceans linger deep below, hidden from the cold. Life, if it exists there, would never know the concept of dawn. They are the ultimate survivors, not tied to stars, not dependent on warmth from above, but carrying their own small flickers within. At the other extreme, there are planets too hot to survive. Some orbit so close to their stars that their atmospheres are stripped away. Others, like KIC 125575448b, are literally disintegrating, leaving trails of dust like cosmic comets. Some are puffed up into giants with densities lower than cotton candy. Others are darker than coal, swallowing nearly all light. Some rain glass, sideways, in winds faster than sound. Worlds are not just solid spheres. They are experiments in physics, each one testing the rules in its own way. Stars and planets are only part of the story. The larger universe is stranger still. Their walls of galaxies stretching billions of light years. Voids so empty they seem unreal. Flows of galaxies moving together as though pulled by hidden hands. There are cosmic microwave whispers from the dawn, still echoing today. And there are future silences waiting, when even those whispers will stretch beyond hearing. We live in the middle of the story, long after the beginning, long before the end. There's an irony in it all. We expect the universe to be predictable, laws written in neat lines, systems in tidy balance. But what we see are exceptions, objects that shouldn't exist, but do, stars that turn into diamonds, planets that fall apart, moons with oceans beneath ice, black holes too large, galaxies too early, structures too vast. The cosmos seems to delight in breaking rules, and in that breaking, it becomes endlessly rich. The sky we see is not only filled with stars, it is filled with memories. Every photon of starlight is a message from the past. The farther we look, the older the message. Light from the sun takes 8 minutes to reach us. Light from the nearest star takes over 4 years. Light from distant galaxies takes billions. When we look outward, we are looking backward. A telescope becomes a time machine. Each faint glimmer is not just a place, but a moment preserved in transit. The oldest light we can see is the cosmic microwave background, the afterglow of the Big Bang. Faint microwaves, stretched thin by expansion, but still carrying the signature of the universe's birth. It is smooth, almost uniform, but not perfectly. Small ripples appear, tiny fluctuations in temperature. Those ripples are the seeds of galaxies. From them, all structure grew. The sky is not just decoration. It is history written in light. But not all signals are steady. Some flash, brief and violent. Fast radio bursts are among the strangest. They last only milliseconds, yet in that instant they release more energy than the sun emits in days. They arrive suddenly, from billions of light years away, then vanish. Some repeat. Some remain forever silent after their first burst. Some follow patterns. Others appear random. Their origins remain mysterious. Magnetars may explain a few, but not all. Listening to FRBs is like sitting in a silent forest and hearing a twig snap once, far away. You don't know what made the sound, only that it was real. Other bursts last longer, but are no less unsettling. Gamma ray bursts, for example, come in two types. Long bursts, from the deaths of massive stars collapsing into black holes. Short bursts, from mergers of neutron stars. Both are violent beyond imagination. They release more energy in seconds than entire galaxies emit in years. If one occurred too close to Earth, it could strip our atmosphere. Fortunately, they are distant, yet they remind us of the scale of power hidden in the universe. Energy enough to unmake worlds, unleash in silence, far from human eyes. There are quieter signals. 2. Gravitational waves, ripples in space-time itself. Predicted by Einstein, confirmed a century later. When two black holes collide or neutron stars merge, they send waves to the fabric of reality. We cannot see them with light. We can only feel them with detectors, long arms of lasers measuring distortions smaller than atoms. The first detection in 2015 was a whisper from two black holes colliding over 1 billion years ago. A faint tremor in space-time, reaching us after its long journey. Since then, we have heard others. The universe, once thought silent, is now a symphony of faint vibrations. Even in apparent stillness, there is motion. Clusters of galaxies drift. Filaments stretch. Entire groups move together in flows we cannot fully explain. One such mystery is the dark flow. Galaxies moving in the same direction, across scales so vast they should cancel each other out. Perhaps they are pulled by something beyond our horizon. Perhaps the universe itself bends differently there. We do not know. But the drift is real, and it reminds us that even the largest scales are not fixed. The cosmos is currents, invisible but undeniable. The emptiness between currents can be stranger than the currents themselves. Cosmic voids stretch for hundreds of millions of light years, containing almost nothing. They are not black holes, not antimatter, just near absence. A few galaxies drift within, but compared to the filaments, they are deserts. To stand in one, if you could, would be to see galaxies only at the edges, clustering on the horizon. The middle would feel achingly empty. And yet, these voids shape the universe. Their gravitational pull nudges galaxies, sculpts filaments, builds a great web of matter. Even absence has weight. Closer to home, the universe experiments with smaller oddities. Cotton candy planets, like Kepler 51b, huge in size but so light they could float in water. Black planets, like Trace 2b, reflecting almost no light, darker than coal. Raining planets, like HD 189733b, where winds blow shards of glass sideways at thousands of kilometers per hour. Frozen oceans, like those beneath Enceladus and Europa, hidden beneath ice but erupting in geysers. Each world a different experiment in physics, a reminder that Earth is not the template, but one variation among countless. Stars misbehave too. Some spin so fast they flatten into oblate shapes, glowing brighter at their poles and their equators. A Kerner is one such star, a cosmic egg rather than a perfect sphere. Others pulse irregularly, expanding and contracting in strange rhythms. Cepheid variables are our Lyrae stars. They keep time with their light, steady enough to measure cosmic distances, yet odd enough to puzzle astronomers still. Some stars are fossils, like the Methuselah star, nearly as old as the universe itself. Others are infants, still gathering mass from dusty cradles. The cycle of birth and death is everywhere, and always the black holes, some small remnants of dead stars, some massive millions or billions of suns in weight, anchoring galaxies, some impossibly large, like TON 618, tipping the cosmic scales at 66 billion solar masses. They warp time, bend space, twist light, orbit them closely, and time itself slows, fall within, and the concept of future loses meaning. They should not exist in such numbers, in such sizes, in such places. But they do. The universe seems to love them, scattering them across the sky like seeds of paradox. What remains when all this ends? When stars fade, when galaxies grow quiet, when black holes evaporate, what will be left? Not fire, not collapse, not noise, only silence, only thin radiation, weak particles, endless time. The dark arrow waits, a universe of stillness stretched across eternity. It will not be a dramatic end. It will be the longest, quietest chapter of all. The story of a universe does not end with stars. After the last suns have burned their fuel, after galaxies have dimmed, another chapter begins. It is called the degenerate era, an age not of light, but of remnants. White dwarfs, neutron stars, and black holes will remain. They will not shine with the brightness of stars, but they will linger, patient and silent. White dwarfs will cool into black dwarfs, their crystalline cores locked in stillness. Neutron stars will spin more slowly, their pulses fading into silence. Even so, matter will endure. Worlds of rock and iron will drift around dead suns. Rogue planets will wander, starless but intact. Black holes will anchor the void. This era will last for trillions of years. To any observer, if such a thing could exist, the sky would appear dark, speckled only with faint embers. The age of starlight will be gone. But the remnants are not eternal. White dwarfs will cool to invisibility. Neutron stars will lose their spin. Black dwarfs will sit frozen, undetectable. Only the black holes will remain, swallowing what little matter still drifts close. They will rule the cosmos in silence, invisible but immense. This is the black hole era. The universe will be dark, except for the faint flickers of radiation around the mouths of black holes, as matter falls in. Occasionally, two will meet, merging into larger giants, sending ripples of gravitational waves through empty space. They will endure longer than anything else we know, but even they cannot last forever. Hawking radiation predicts that black holes are not permanent. They leak energy, particle by particle, across unimaginable spans of time. For stellar mass black holes, the process takes 10 years, a number so vast it dwarfs the age of the universe today. For supermassive black holes, the timescales are even greater, 10 superscript 1 years or more. Eventually, even the largest will shrink, collapse, and vanish in a final flash of faint heat. The universe, once filled with stars, galaxies, and light, will have no stars left, no galaxies, no black holes, only particles. Then begins the dark era. Matter itself may decay. Protons, the building blocks of atoms, might not last forever. If they do decay, over 10 superscript 3 years or more, then all that is solid will eventually dissolve. Planets, rocks, even the black dwarfs will vanish, reduce to radiation. If protons are eternal, the remnants will persist, drifting endlessly, but cold and still. If they decay, the universe will be reduced to nothing but electrons, positrons, photons, and neutrinos, particles scattered thinly across an expanding void. Time will not end, but events will. In this far, far future, the universe will be almost entirely silent. No stars to rise, no galaxies to spin, no collisions to stir gravity. It will be a sea of darkness, sprinkled with faint particles so sparse they may never meet. Temperature will approach absolute zero. The very fabric of the cosmos will stretch thinner and thinner until nothing happens at all. It is the longest era, the quietest chapter, the final stage in a story that began with fire. And yet, there is a strange poetry in it. The universe begins with noise, with light, with expansion so fast it defies comprehension. It grows wild, birthing galaxies, stars, planets, life. It blazes with quasars, supernovae, and bursts of radiation. Then, gradually, it settles. It calms. It cools. Until, finally, it rests. Not destroyed. Not broken. Just still. There's a chance, however, that the story is not so simple. Some theories suggest that dark energy may grow stronger with time. If that happens, the expansion will accelerate without limit, tearing apart galaxies, then solar systems, then atoms themselves. This end is called the Big Rip. Others imagine the opposite. That expansion may one day slow, reverse, and collapse in a big crunch, folding all matter back into one. Still others wonder about cycles, expansions and contractions repeating forever. For now, evidence suggests a quiet fade, eternal expansion, eternal cooling, eternal silence. It may not be dramatic, but it is steady, and in its steadiness, it is strangely peaceful. Think of the objects we have seen along the way. Diamond stars, crystallized remnants of suns, worlds of glass rain, sideways in storms faster than sound, moons that should be frozen but spout geysers into space, planets lighter than water, darker than coal, black holes larger than models allow, galaxies older than they should be, structures larger than cosmology predicts, each one improbable, each one breaking a rule. The universe is not just a machine. It is an improviser, creating variations, exceptions, contradictions. And all of it, one day, will be memory only. But for now, we are here. We live in the stelliferous era, the age of stars. We look out and see a sky crowded with light. We build telescopes, write theories, and listen to the faintest whispers. We are alive in a brief window when the universe is both visible and understandable. Not too young, not too old. The perfect age to ask questions. Perhaps that is its own kind of miracle. Even as the universe dims, there will be survivors. Stars may die, galaxies may fade, but some objects endure longer than we expect. They are the wanderers, the drifters, the quiet holdouts against eternity. One group are the rogue stars. Normally, stars belong to galaxies, bound in spirals or ellipticals, orbiting within clusters. But sometimes they are flung free. A close pass with a supermassive black hole or the violent tug of galactic mergers can eject stars at thousands of kilometers per second. They are cast out, stripped of their companions, left to travel the void alone. Some may carry planets with them, whole systems torn from their homes. Imagine a planet orbiting a star that drifts endlessly between galaxies, never again seeing the crowded sky of a spiral arm, only the thin scatter of distant light. To us, rogue stars are faint, hard to detect. But they are there, lighthouses wandering in a sea with no shore. Other survivors are even stranger. Rogue planets, ejected from their stars, drift alone. We have already found a few, and estimates suggest there could be billions in our galaxy alone. Some models even predict trillions. They are orphans of the cosmic dance, lost during the rough play of planetary formation or the gravitational violence of stellar migration. On their surfaces, darkness reigns. No dawn, no dusk, no seasons. And yet, deep beneath, heat may persist from radioactive decay, from tidal flexing, from ancient warmth that refuses to die. Under thick ice, there could be oceans. Life, if it exists, would never know the word sun. These worlds remind us that habitability does not mean sunlight. It means persistence. The skies still hold their own oddities. Some exoplanets are lighter than physics seems to allow. Kepler 51b, for example, is almost as wide as Jupiter but hundreds of times less massive. Its density is like cotton candy. A giant balloon drifting through the sky of its star. Others are darker than imagination. Trace 2b reflects less than 1% of the light that hits it. Blacker than coal, darker than asphalt, nearly invisible in space. Some rain glass sideways, driven by winds faster than sound. Others hold seas of methane instead of water, with rain and rivers made of liquid hydrocarbons. The universe is not short on imagination. Even stars continue to surprise us. A Kerner, for instance, spins so fast it bulges at the equator. From afar, it looks stretched, brighter at its poles, dimmer at its waist. We think of stars as perfect spheres. A Kerner reminds us that motion bends perfection. Some stars pulse instead, swelling and shrinking in regular cycles. Cepheid variables keep time with their rhythms, steady enough that astronomers use them to measure distances across galaxies. Others are older than they should be. The Methuselah star, HD 140283, appears nearly as old as the universe itself, a living fossil, carrying within its composition the chemistry of a cosmos not yet rich with heavy elements. It is humbling to realize that even after billions of years, stars can still defy our calendars. Galaxies also leave us puzzles. We have found some with no dark matter at all, systems where stars move only as visible matter predicts. They should not exist if dark matter is universal. But they do. Perhaps they form differently. Perhaps dark matter clumps unevenly. Or perhaps gravity itself behaves differently at these scales. Each possibility rewrites the rules. And the galaxies drift on, unbothered by the confusion they cause. Other structures are so large they test belief. The Hercules, Corona Borealis Great Wall, stretching 10 billion light years. The Sloan Great Wall, hundreds of millions. The filaments of the cosmic web, binding clusters together like threads of silk. These formations should not exist at such scales, not under our simplest models. Yet they do. The universe does not flatten evenly. It clumps, knots, weaves itself into shapes larger than we can imagine. And between those knots lie voids, vast, nearly empty regions, so large that entire galaxies look like dust specks at their edges. It is a pattern both simple and strange. A sponge of matter and emptiness, repeated across billions of light years. Even as the universe fades, these patterns will remain. The cosmic web will stretch thinner, but its structure will linger. Clusters will drift further apart. Voids will grow wider, but the web shape will persist until galaxies themselves dim. And after that, the black holes will reign. For trillions of years, they will swallow matter, merge, and distort space. Occasionally, two will meet, and gravitational waves will ripple outward. But slowly, inevitably, they too will fade. Their end will not be sudden. It will be patient, particle by particle, through Hawking radiation, until nothing remains. And so the universe will enter its final age, the dark era, when only thin radiation and faint particles remain, when no stars shine, no galaxies glow, no black holes anchor gravity. It will not be an end. Exactly. Time will go on, but events will grow rarer, then nearly non-existent. It will be a cosmos of silence. It is difficult to imagine such a universe. Our skies are full, our nights crowded with stars. Even the emptiest deserts on Earth are rich with light above. To imagine a sky where nothing shines is to imagine absence beyond absence. And yet, that is the likely fate. The cosmos began with light, and it will end with dark. But here we are, in between, living in the brief, bright middle. When the last stars fade, when the galaxies fall silent, when even the black holes vanish, the universe will not end. It will keep going, stretched and thinned, carried onward into a future almost beyond imagination. This is the dark era. There will be no suns, no shining nebulae, no galaxies glowing in clusters. Only the remains, faint particles scattered across a space, so wide that they rarely meet. And yet, even here, there are questions. One mystery lies in the fate of the proton. Every atom we know, in your body, in Earth, in stars, is built from protons. For decades, physicists have wondered, are protons eternal? Or do they decay, given enough time? If protons are stable, then matter will endure forever. Black dwarfs and neutron remnants will drift endlessly, frozen monuments in a dark universe. But if protons decay, then even matter itself will not last. Over timescales of 10 superscript 3 years or more, atoms will dissolve, their particles spreading as radiation. Planets will vanish. Stars' remnants will dissolve. Black dwarfs will crumble. The very building blocks of substance will unravel. If this is true, then nothing solid will remain. Even without proton decay, the future is quiet. The black holes, once thought eternal, will evaporate. The smallest will vanish first, the largest last. The behemoths at galactic centers, billions of solar masses each, will linger longest, evaporating over 10 superscript 1 years or more. Their ends will not be dramatic. No explosion, no collapse, only a faint glow, a trickle of radiation, until they fade completely. The universe will lose its last anchors. Gravity will no longer gather. Everything will drift evenly, thinly, silently. And what remains? If protons endure, the universe will be filled with frozen husks, black dwarfs, neutron stars, white dwarfs, drifting forever. They will not shine, but they will exist, a gallery of silent remnants. If protons decay, then even those husks will vanish. The universe will contain only electrons, photons, neutrinos, and faint radiation. A soup so thin it may never form structure again. Temperature will approach absolute zero. Motion will slow. Events will cease. Not destruction. Not collapse. Just stillness. It is tempting to call this an ending. But time itself does not end. It stretches forward endlessly, even when nothing happens within it. The universe will not stop. It will simply empty. A stage set for a play that never begins. And yet, even here, imagination lingers. What if dark energy is not constant, but grows? Then the universe could face a big rip, where expansion accelerates until it tears apart galaxies, stars, planets, even atoms themselves. What if expansion slows, reverses, and collapses? Then a big crunch would gather all matter into one dense point, perhaps igniting a new Big Bang. What if cycles repeat, eternally? Bang, crunch, bang, crunch, an infinite heartbeat of universes. Our evidence points to the quiet fade. But the future, like much of the cosmos, remains uncertain. In some ways, it is fitting. The universe began with light too bright to look at. It may end with darkness too deep to notice. It began with noise, the roar of expansion, the fire of creation. It may end with silence, the calm of eternity, the settling of everything into stillness. Between those two extremes lies everything. Galaxies, stars, planets, oceans, forests, questions, and us. We live in the brief middle, when the universe is neither too young nor too old, when light still travels to us, when questions can still be asked. This moment will not last, but it is ours. Imagine standing beneath the night sky. The stars above are bright, the galaxies faint but real. They are the survivors of billions of years of creation. They are the ancestors of silence. One day, all will fade, but tonight they shine. And that is enough. The universe is vast. It is older than every story we tell, larger than every map we draw, stranger than every thought we form. And in its vastness, it has created things that should not exist, yet do. A star of diamond, frozen in stillness. A planet raining glass sideways in winds faster than sound. A moon erupting with geysers from an ocean hidden in the dark. A galaxy that formed too soon. Another that lost its dark matter. Another that stopped making stars before it should have begun. Black holes heavier than galaxies. Walls of galaxies stretching across billions of light years. Voids so empty they seem unreal. If we had written the rules, none of these would have appeared. Yet here they are, steady in the night sky. We began with fire. The Big Bang, the birth of light, the first atoms, the rise of stars and galaxies. The universe grew restless, noisy, crowded with blazing suns, swirling clusters and bursting supernovae. We live in the middle of that story. Not the beginning, not the end, but in the brief chapter where stars still shine, galaxies still glow, and light still reaches us. One day this age will pass. Stars will fade. Galaxies will empty. Black holes will dissolve. And the universe will drift into silence. But not yet. Tonight, the sky is still full. Every point of light above you is a survivor. Every galaxy is a story. Every signal, from quasars, pulsars, bursts, and whispers, is a reminder that the cosmos is alive with variety. The silence may come, but for now, there is still sound. The darkness may arrive, but for now, there is still light. The stillness may reign, but for now, there is still motion. We are here, in the middle of the blaze. There is something quietly humorous in it. The universe is enormous, yet we, tiny creatures on a small planet around an ordinary star, have noticed. We have built telescopes, launched satellites, tuned radios, and caught whispers from billions of years away. It is as if ants, crawling on a pebble, lifted their heads and began mapping the mountain. And somehow it works. Our questions reach farther than our hands. Our minds stretch wider than our eyes. We are part of the universe noticing itself. The things we have seen are improbable. Stars that become diamonds. Planets lighter than foam, darker than coal. Moons alive with oceans. Galaxies arranged in walls too vast for reason. Black holes so massive they bend imagination. And still, the universe holds more. We have not seen the edges. We have not mapped the end. We have only skimmed the surface. Perhaps the greatest strangeness is not what we know, but how much remains unknown. And yet, there is calm in this uncertainty. The universe is not rushing. It moves on timescales so vast that our entire history is a blink. We can ask questions without needing all the answers. We can listen without needing to hear the end of the story. We can rest beneath the stars, knowing they shine for now, and that now is enough. Imagine lying beneath a night sky. The stars are steady. The air is quiet. The earth turns slowly beneath you. Above, galaxies glow faintly, far beyond your sight. They are there, regardless of whether you see them. They are old, regardless of whether you know them. They are strange, regardless of whether you understand them. The universe does not need our permission to be strange. It simply is. And so we end this journey, not with noise, but with stillness. The universe will fade, but it is not gone yet. The stars will die, but tonight they burn. Silence will come, But for now, there is light. It is enough to rest in this moment, to listen to the quiet rhythm of galaxies turning, stars burning, planets drifting, to smile at the strangeness, to marvel at the impossibility, to relax into the vastness, because the universe is not in a hurry, and neither are we.